Going to take a look at section 7.7, so continuing in chapter 7 of the textbook. And we're going to be looking at this thing called dot product. So we're still in our world of vectors. And now we're going to look at some ways we can find information about vectors. And then ultimately in physics, there's tremendous applications of this dot product. We won't get into. We're going to just look at some of the basic ideas concerning dot product. So dot product, as you can see here, is going to involve two vectors. In this case, we're going to name these vectors vector v and vector w. And the I and j components are a1 and b1 and a2 and b2 for these two vectors. The dot product is written as v, no surprise here, no tremendous imagination, v dot w. And that represents the dot product of these. And what that dot product is made up of is the product, or you multiply a and a. So a1, you multiply the I information, and then you multiply the b information, that's here, b1, b2, and the dot product is the sum of the products of a1 and a2 and b1 and b2. So you multiply the I information, you multiply the j information, and then you add the results of those two multiplications. Note here that the dot product is a scalar quantity. That means it's a real number. It is not a vector. So we're going to be using vectors to find the dot product, but the answer is just a number. It's not a vector. As usual, we'll take a look at some examples on how we would find these. So in this first example, we're looking at v dot w. So vector v dot w. So we multiply the a, so we have 7 times 2 plus, and now the j information, -4 times -1. So that's the multiplication we're going to do. 14 plus 4, negative is positive, 14 plus 4 is 18. So the answer, you can see it's not a vector, it's just the number 18. Now let's take a look at finding the dot product in the reverse order with vector w dot vector v. And so it's going to be 2 times 7 plus -1 times -4. So the same information, it's a times a and a times a and b times b from the j component, but now the order is reversed. 2 times 7, we have 14 plus 4. When I say the order is reversed, instead of 7 times 2, it's 2 times 7, but we can see we get the same products, and so we're going to get the same answer, 18. So when we add them, we get the same dot product. Now, what about vector w dot vector w? So here we're looking at w, so it's going to be 2 times 2 plus -1 times -1. 2 times 2, we have 4. -1 times -1 is 1, and we get the answer 5. So I think you'll find that the calculation of a dot product is pretty straightforward there. Let's take a look at, I know you can read these, but let's just take a quick look at some of the properties of the dot product. If you have two vectors, u and v, the dot product u dot v is equal to v dot u. So you could see that in this example above. If you have two vectors, you'll get the same dot product regardless of the order of the vectors. In this next property, if we have three vectors here now, u, v, and w, if we add vectors v and w first, and then find the dot product between that resultant vector and u, that will be the same as if we find the dot product of u and v, and then the dot product of u and w and add them. So this kind of looks like the distribution property that we've used before in algebra. The zero vector dot product with v is just going to give 0. I think that's almost common sense. V dot v, when we find the dot product of a vector with itself, that number is equal to the magnitude of that vector squared. So going back here, if we were to find the magnitude of vector w here, we would find that the magnitude of w is the square root of 5. And when we square the square root of 5, we get we get 5, which is the dot product. So that's what that statement there is saying. And last but not least, in the properties, if we have some c, some scalar number that we are multiplying with a vector w, a vector u, and then we are finding the dot product of that, this is now a vector, it's been multiplied, but it's still a vector, with the dot product of vector v, that is going to be the same as if we find the dot product of u and v first, and then multiply it by the scalar c, or we might multiply v, vector v, by the scalar c, and then find the dot product. So when you do work with vectors and dot products, sometimes it can be useful to remember these formulas because the calculations might be easier to take one of these approaches than one that you might have without using these properties.